So now we will start to analyze and understand the processing of the network and how it will learn. So firstly, we'll need to define some concepts. Okay, here, as you could know, we have this, that is the input layer, this, that is the hidden layer. Okay, this is another way to visualize a network, and this is the output layer. Why each hidden layer has two neurons here? Because it will have two states. One will be an inactivate neuron and the second will be an activate neuron. So I have divided each neuron here into two neurons. Okay? So here we can see that a neuron is defined as something like this, where I is the position and L is the layer where the neuron is. So here we have the neuron x11, here the neuron x21 because it's in the position 2, and the next the same in the next layers. Also, you can see here that we have some connections, okay, and these connections has also a notation. This notation consists of a connection that in this case in neural networks we call the connections weights because they have associated a value. We'll have the direction of the connection. So for example, if we have 1 1, it says that the connection is between neuron 1, okay, to the neuron J, okay. So here we have the connection 1 1, so it will be from neuron 1 to neuron 1 to of the second next layer. So if we define this as this, we'll see that it will be the connection from the neuron in this position to the neuron in the position J of the next layer. Okay, perfect. So the next thing is that values will be stored in each of these elements of the network. Here we'll have associated a value, and also in each weight we have associated a value. I haven't said to you, but also we have an extra neuron on each layer that will be the bias. The bias notation will be the same as a neuron, okay? And will be the B, the position of the bias, and the layer, okay? As you have seen here. This extra neuron, okay, will have connections, will be fully connected also to the next layer. And the biases will be the weights that this bias is connected with. And this might be very complex, but when we see the algorithms, it will be more easier. So now, the next thing we need to know is that we will apply some functions, okay, to the input data to calculate the output data that is in the output layer, that we say that is here. Okay, so this function will be f in the first layer. For example, I have defined f, and it will be from dimension 8 to dimension 2. Why? Because we have a lot of parameters here, because we have these connections, these neuron values, and also the biases, because this is not a value, okay? So it's not a parameter of the function. So it will be a vectorial function that will have in this case these neurons and also the weights that are these, and finally the biases. So we'll have a function that will have 8 parameters. So it will be from height, okay, to dimension 2, because we have two output, okay, that are the net x1 2 and next x2 1. Why here we don't have x and we have the prefix net and out? Well, as I said, a neuron has two activation values. So we can divide a neuron as the net, that is an activated and an unactivated value, and the out, that is the activated value. So when we apply this function, we will calculate with these values, okay, these values that are here, we'll calculate these values, okay. But now, what do we need to do to calculate the out? Because now we know the net value, that is the unactivated value. We will apply a function that is the activation function, and we will have a lot of plenty of activation functions, but in this case we will use the sigmoid function, that is an application from real numbers to real numbers, okay. This activation in this case, we will define it as we will pass the net value, okay, so here we have the net of a neuron, and we will calculate the out value. In this case we will define the function as this function that is widely used and is called the logistic function. And if we see it in a graph, in a graphical, we can see that it's something similar to this, okay. So from values that are very proximate to the zero, it will have more variation and it will be more sensible than values that are far away from the y-axis, okay. So the limit here, when x tends to infinite, will be of this function will be infinite, sorry, will be 1. However, when the value goes to minus infinite, will be 0, okay, and we'll have the values from 0 to 1. That is what we want also.